Hello and welcome to this new episode of Bootstrapping Your Dreams Show. I'm your host Manoj Agarwal, and today we are going to have a very fascinating conversation with Zaheer Ali. So Zaheer is a world-renowned innovator and leader who currently works for NASA's SOFIA, which is full form for short for Stratospheric Observatory for Infrared Astronomy, as the manager of safety and mission assurance. SOFIA is an advanced telescope mounted on a modified 747 Boeing aircraft which flies to 45,000 feet to do infrared astronomy. Zaheer is also a celebrated TEDx speaker and thought leader in management and technology practices. With over 500 million in captured contracts, he has worked with the US Department of Energy, US Department of Defense, NASA, DARPA, and other agencies. Zaheer has been working in the University Space Research Association, USRA, for the last 10 years. Amidst the COVID 19 pandemic, he led USRA Sofia back to work in close collaboration with NASA and international partners, making them the first suborbital program to return to operations and deploy internationally. Zaheer is also the co founder of the National Center for Nuclear Security, worked as a principal investigator, and held a short director's position at the lab for laser energetics of University of Rochester. His list of achievements keeps going on, as he's also consulted as a micro and nano device engineer. Along with all this, he has co-founded numerous startups and takes out time to mentor the youth and champion for inclusion and justice. Welcome to the podcast, Zaheer. I'm so excited to talk to you.
Thank you very much, Manoj. It's a pleasure to be here, and thank you for your kind words.
Yeah.
That's it's very kind. Thank you.
No, you have a huge list of accomplishments, and I want to get to know you a little bit, your journey. So, how did you get started? I'm a self-proclaimed space fanatic, but how did you get into it? How did you reach the stage, the level of success that you are at right now?
Well, I mean, I've done some things in my career, and I'm very lucky. I've been very fortunate. What got me started was having. I was one of those people who wanted to know how things worked.
Mhm.
And I was lucky enough to have parents and people around me who encouraged that, who
Mhm.
didn't get annoyed with the why does this work this way or why is
Yeah.
that way, and would tolerate me having strange concoctions that were supposedly chemistry experiments underneath the bathroom sink, or or taking apart something that I really shouldn't have because I
Yeah.
wanted to look at what the heck it was made of.
Yeah.
Children need to be encouraged in that regard,
Mhm.
and there are those of us who make a difference by being able to aggressively be curious. And curiosity and encouragement of curiosity in children is, in my opinion, one of the biggest benefits you can give them and
Of
help them be
course.
successful in the world.
Yeah, for sure, for sure. And so from there, uh, doing all these discoveries during your childhood, how did you get to NASA and what you're doing right now?
So one of the things that was key for me was having access to knowledge. And nowadays, with kids, they've got the internet.
Yeah.
Not just for video games and chatting with your friends, but it's actually more knowledge than has ever existed in the world, more accessible than
Mhm.
has ever been possible before.
Yeah.
But for me, it was libraries and books, lots and lots and lots of books. But it's also experiences. My parents made a point when I was a kid of saying, "Look, you can be late to school today. It's more important you watch this shuttle launch,
Oh, nice.
right?" Because and they gave me an excitement. They gave me a sense of the achievement of these things,
Yeah.
what they really meant. Not just that it was something somebody else was doing, but that it was something that belonged to all of us as human beings.
Yeah.
And so later on, when I got to other parts of my life, high school, and then college, I was eager to do not just to read or learn. And that eagerness to do and to get my hands dirty turned into internships very early in my college career. And I have mentored a lot of young people. I've been lucky enough to have young people in my life means that I get to stay, part of my brain gets to stay at 20 years old, right?
Yeah.
And what I have found is that when I can push them into getting internships early, it makes sure that they have great careers. However, and oftentimes you pivot around. So I started by being fascinated by the world, and I didn't major in astronomy. I majored in physics because I was more interested in the fundamental ways things worked than necessarily looking at the stars. But understanding the way things worked led me to the stars. And I was also fortunate enough to have some guidance from mentors early on who were mentors through my internships, who told me to make sure I took plenty of courses outside of my major. So as a physicist, I took a tremendous amount of nuclear engineering and electrical engineering. I took chemistry. I took chemical engineering. I took materials. And what that did was it gave me the capability to be very useful to people who needed things done very quickly. And that made me able to get the next internship and so on and so forth. So it laid a career out for me in a way that I think not all students have the benefit of. Not necessarily, in my opinion, because I was so special, but because I got good guidance and I listened to it. So, I'm always trying to tell young people, what can you do that will make it so that somebody who has something they need done is willing to take a chance on you as a 19-year-old or a 20-year-old or even as a 25-year-old, whatever. What can you do? And focusing on the doing and less on the talking or the writing at some point basically made me successful.
That's awesome. Beautiful. Yeah, I mean, a few points you brought up, the value of mentors and guidance, especially from your parents early on. I think that was invaluable. And I talked to all these global leaders, and almost everyone mentioned how important mentors were in their life. And the other thing that you mentioned was, dabbling in different topics, different subjects, gives you a different perspective than other people who focus on one area. So
right.
I think that's a very good point. And actually following through with that advice is another thing, because we all get a lot of advice, but to actually follow through is rare as well. So that's great that you took action. Now let's talk about SOFIA first, because it's just fascinating. I heard about this like a few years ago watching Discovery Channel. I was like, wow, mounting a telescope on the airplane. How did that happen? Like, what is the purpose of that? Why can't the telescope, first of all, stay on the ground? And what is infrared astronomy?
Sure. So I'll start with the why, because I think that's always the best place to start. Why would we need to put a telescope anywhere but on Earth? So so we'll start with what infrared means. So when you think about the electromagnetic spectrum, you have the light that we see. And we don't see that much of it. It's a very small amount of all the electromagnetic radiation that's whizzing around in the world. We see a very narrow band. That band we call the optical band, because it's literally what our capability optically is. And those are the colors of the rainbow, right? Red, yellow, orange, etc., all the way up through violet. And then we've heard of UV. UV's been in the news a lot recently because it kills coronavirus. It turns out, right? And they have deep UV and UVA, B, etc. What the color of light fundamentally represents is the energy. There is more energy in a beam of blue light than in a beam of red light. There's more energy in a beam of violet than in a beam of blue, and hence ultraviolet is even more energetic.
Yeah.
Infrared, infra from the Latin or the Greek, lower than red, is less energetic than red, and we don't really see it.
Yeah.
But it's there. Often we think of it as, oh, infrared energy is heat, mostly because oftentimes what is called thermal energy, things that radiate heat, radiate in the infrared.
Yeah.
And that's kind of a shorthand. So when we talk about infrared, we're talking about energy that is less energetic than a red laser, but more energetic than, say, a radio. And so that band, the infrared, from just below red all the way to the radio, and there are different bands. You slice up that part of the spectrum into near IR, near infrared, meaning it's close to red, close to optical, mid, and then far. Infrared is really well blocked by water.
I see.
So if you want to test this, a fun little test is to take your TV remote, put a glass of water in front of it, and try to see if it'll work.
Oh, nice.
I don't put it in there. Okay, that'll promote the circuit. All right, that's not a good idea, guys. I didn't say put it in the glass of water. Put it in front. Okay,
Yeah.
Put it in front.
Yeah, thanks for clarifying that.
Or take 2 or 3 bottles of water and put them there and try to do that. Now, and if it's close enough, it won't work because it's being blocked. And what happens is that the infrared light coming from the universe is blocked to a great extent by the water vapor that hugs close to the Earth. That's humidity, right? We all know, on a cold, wet day, it actually is pretty wet, right? Or on a hot day, in the tropics, say you're in Hawaii or you're in India or where have you, a nice vacation spot like Bali, whatever. It's humid. That humidity is blocking infrared.
I see.
So to get above that, you have to get your telescope above that, even on the top of a mountain, Mauna Kea in Hawaii, where we have several telescopes.
Yeah.
You still only get about 20% transmission, and then you only get it in the more energetic part of the band. That's the near infrared. The mid and far are basically blocked.
Got it.
So what do? You go up, and you can go to orbit, but it costs a lot of money to get to orbit. Those missions are very high risk, and they don't last very long because of the various systems. Typically, Hubble is an exception, but keep in mind, Hubble did not do much in infrared. It was primarily an optical telescope, meaning the same wavelengths that we see with our eyes. The reason to go up to Hubble altitudes or to orbit for Hubble was to have the ability to do work that you can't do from a stationary location on Earth, and to get rid of atmospheric speckle. So the atmosphere just absorbs enough light that you can't get those beautiful deep field images where you're basically looking through vacuum all the way to infinity, to infinity and beyond, perhaps. And so we need, as a team doing infrared astronomy, we need to get up to where the signal is. Turns out the tropopause, which is the altitude level where you get out of the troposphere, which is the water vapor layer, it typically goes between 35 and 50,000 feet. And using 747 SP, people often ask me, the aircraft looks funny, it's a short one. Did you guys take out a section? We did not take out a section. It's a 747 SP. These were built in the 1970s specifically to have a better fuel to distance ratio, and they simply did it by taking mass out of the aircraft. And also, they are built to cruise at a high altitude. The engines are special Pratt & Whitney J's. These engines were built for thinner atmosphere. They're not as efficient as the modern engines from GE, Rolls, or Pratt & Whitney, but their cruising altitude is far higher, and that was perfect for us. So NASA acquired a 747 SP, and they underwent a program to do major surgery. When we first went into operations, it was the most heavily modified aircraft in the world.
Wow.
At least unclassified, that is.
Yeah.
And it probably still is. It's a Frankenstein's aircraft, right? But it's a piece of art because it works and it generates amazing results. Like last fall, the water on the moon, the water on the sunlit side of the moon that we found, that we're going to go back and do more measurement of in support of the lunar missions that NASA is ramping up to do. Ideally generating some sort of map of density and locations. So that's why we have to go up there. And that's why the aircraft was modified to put a telescope inside of a jet and to fly it at a high cruising altitude to get above the water vapor so that we could do this very specialized type of science that opens our eyes to a whole new universe because we can see different types of light.
Amazing. That's amazing. All right. So the next question then is to fly a plane and to observe far away objects in the universe, you need to stabilize the telescope, isn't it? Like even if we take a photo or shoot a video with our mobile phone or camera, we see blurs, and there are things where we can stabilize the image or something so that we can see it clearly. I'm sure this is a much bigger problem for you, is because the actual plane is also moving. So how did you handle that?
So this is a spectacular feat of engineering. There are really three key parts of the observatory in terms of hardware. There is the aircraft itself. There is the telescope or what we call the telescope assembly. And then there are what we call the science instruments. You can think of them as very, very specialized custom cameras, basically.
I see.
So this is a question about the telescope. The telescope itself, it was the contribution of the German partners to NASA. So this is a joint NASA and DLR program. NASA partnered with the German Space Agency. That's what DLR is. And they developed this telescope and what is called the vibration isolation system. So there are two parts of this. First of all, there is the vibration isolation system, which is very similar to air ride trucking technology. It's what's called bladder on bladder. And this isolates macro vibrations. So takeoff, landing, keeps the whole system from being shaken to heck, right? But the elegant, beautiful solution to keeping the flight vibrations out of the telescope, or out as much as possible. It's not possible to completely decouple, as long as there's mechanical connection, which obviously there is, was they took the entire 17-ton telescope and it is mounted on a spherical bearing, kind of like a gimbal joint. That bearing is then pressurized with oil so that the entire 17 tons floats.
Oh my goodness.
On a layer of oil thinner than one of my hairs.
Wow.
It is remarkable. And the telescope, between where the lens is and where the cameras are, is so perfectly balanced that you can move it with your pinky. I've done it. It is a feat of engineering. Why in the heck do we need to balance it that well? Because what happens is when the aircraft airframe and things just in flight are moving around, that bearing is inertially locked onto a target.
Got it.
And the aircraft is moving around the telescope.
I see.
It allows the aircraft to bend and twist and jiggle around the telescope. What, in my opinion, the most spectacular demonstration of that, of how effective this is, was a few years ago, and you can check this out on the NASA SOFIA Facebook page. It's a spectacular and it was a fun experiment. We did it because we thought it would be cool. And then those things happen when you're a bunch of scientists and engineers. We mounted a camera on one of the workstations looking at the telescope, and we mounted a camera at the telescope looking back at the workstation. So we have these two camera recordings, and in each one, it looks like the other thing is completely bouncing around. So, for
Nice.
example, when you're sitting there at the telescope operator's workstation and looking at the telescope, it looks like the telescope's going everywhere.
Yeah, yeah, yeah.
Now, the camera on the telescope looking back at the cabin, it looks like the cabin's going everywhere.
Yeah, yeah, yeah.
Which one's right? Which one is actually the one moving? Well, we also put accelerometers next to the cameras.
Mhm.
And when you look at the two accelerometer traces, the one on the camera is basically flat. Or sorry, the one on the telescope is basically flat.
Wow.
The one on the workstation in the cabin is going everywhere.
Oh my
Proving
goodness.
that it's the aircraft moving around the telescope.
Yeah, yeah, yeah. That's amazing. That's awesome. Yeah, I can't even imagine thinking of a solution like that and actually implementing it. Like engineering is hard, and I know by experience. So it's just amazing what these modern machines and us humans can do basically. Now, what is the most interesting thing that you have found using SOFIA?
I actually am a huge proponent of lunar and Mars exploration.
Mhm,
So my favorite results are the water on the moon, which was very recent, and then a couple. Maybe I've been on the program for 10 years, so it blurs a little bit.
Yeah, yeah,
It might be more than a couple of years back. But we did a very interesting observation looking at the hydrogen ratios on Mars.
Mhm.
And those are very important because they help us understand where hydrogen and different types of hydrogen are on Mars, in the Martian atmosphere, or on the soil, and could help determine where we want to land, where we want to set up a colony, and where we're going to have the best ratios to convert atmospheric hydrogen from
fuel.
Mars into fuel.
Yeah, cool. That's
So,
awesome.
so those to me are really exciting results. But I have to be honest, there have been some other really spectacular results. For example, the helium hydride, the first molecule, going back, one of the first molecules going way far back, close to the Big Bang, and also the results understanding how magnetic fields may be quenching the influence of the black hole at the center of our galaxy. I urge our viewers to go ahead and check those out. www.sophia.usra.edu. Sophia.usra.edu has all these results, amazing pictures and view graphs that you guys can check out.
That's awesome. I'll add that link to the show notes.
Thank you.
And okay, so now then the next question, I always ask anybody I talk to about space is, how about what do you think about extraterrestrial life? What do you think? Like, do you believe in it? What are your views?
I certainly believe in the possibility. I'm a physicist trained, and what that means is that I try to believe very little, keep my mind open about everything, and trust the results, trust the science. We have not yet confirmed that there is life anywhere else in the universe, but that does not mean that it isn't. The universe is huge, and there are more planets that could support Earth-like life than we can count, probably. And that's just Earth-like life. That does not include types of life that we don't really have a good way of even conceiving yet, because they're just what they could be are so foreign to us. That's the realm of science fiction or science speculation, perhaps. But I always tell people how much of what we have now was completely something that would have been science fiction just 100 years ago, or less than 100 years ago.
Yeah, for sure.
So it's something to keep in mind. I defer to the greats, Sagan and Drake, who developed different models of thinking about the likelihood of us being alone, and also of us making it to the point where we could contact another civilization. There are two ways to work that equation: the Drake equation, for example, or the Sagan model for civilization development. So those are fun things to think about. If we're going to find something in our solar system, it's going to be something small. It's going to be something that we're going to have to find 10 times to verify that we really found it, that we didn't take it there with us on accident. Which is why the clean rooms at the space research centers exist, and why people are so obsessively careful at this point. We found out that some of our lichen went to the moon and back, amusingly enough. So, the possibility of us taking something somewhere is very real. And so we have to be very careful. At the same time, it is exciting. The recent results from Venus, which now unfortunately look like it's just going to be something that's an atmospheric effect, but they were tantalizing. They were truly tantalizing. Could there be atmospheric microorganisms in the atmosphere of Venus? And we're going to continue to find results that are tantalizing, and there's a non-zero probability that one of those is going to be real.
I'm excited about that. And you're absolutely right. Like, even on Earth, we are finding new species all the time. We are finding extremophiles and in all kinds of places. So it's just amazing where life can take hold. And you spoke about and then the other aspect is, like, I wonder about the psychological effect of that event. Let's say if we do find extraterrestrial life, how will it affect us as a species? Because we think that we are the only ones, but once we find something else somewhere else, it's like one of many, right?
I don't think that, for me, finding life could exist elsewhere or does exist elsewhere would give me any type of identity crisis.
Oh, really?
And I think what will happen, I hope will happen, is that such a discovery brings us together.
Exactly, that's what I mean. Not at an individual level, but at a like a species level.
I think it'll force us to realize how fragile we are, how fragile our planet is. Even if there are infinite species out there, because the universe is infinitely large, they're not close to us. On this pale blue dot, as Sagan put it, right? We somehow exist. And anybody looking from anywhere else has no idea of all the trials and tribulations, joys and sorrows and great triumphs of all the billions of people that have ever existed. And nothing we discover out there is going to change that. So, if anything, I hope it brings us together. But I think most of us will address it with equanimity, because it doesn't really change anything.
Well, let's hope so. Let's hope so. You are in a field where it's sort of it's sort of accessible to you to think about it. But I think 99.9% of the population do not think about it, and I think it'll force them to think about that fact, right?
I think maybe that would be good for them.
Yeah, exactly.
But I tell you this, Manoj, people have said that when life outside of Earth is discovered, it'll be the greatest discovery ever of mankind, and I completely disagree. It's important, but when I look around at our world, I think the greatest discovery of humankind would be fusion, power source, or faster than light travel. I think things that enable us to do more are the great discoveries.
True.
Finding life somewhere else is just another road marker. Great. Okay, we found some little primitive amoeba. Whoop-de-dee. Now let's go look for more. Right? That's really going to be, I think, the attitude that we're going to have and want to have. And in terms of great discoveries and what things will mean for people, I think if we discovered a faster than light transport method, or even the possibility that it's real, and there's some new papers out that are hypothesizing ways for that to exist, that truly revolutionizes our capabilities in the universe. Suddenly we can go to an asteroid instead of in decades, in minutes. Now that's a game changer, right?
Let's see. Let's hope that happens soon. And you talked about Mars, and there's a huge debate on Mars. Some people say, hey, let's just at least fix our own planet before we go out there. And I mean, the idea is they're saying, and I sort of agree with that, is like we have already ruined one planet. Why do we want to ruin another one? So, what are your views about it? Like, why do you think that it's a good idea to go there and colonize it?
I think people who say that are short-sighted and ignorant of what the space race has given them.
Mm.
People who say that often do it on a smartphone. Well, guess where that came from, sir or ma'am? You don't understand that it is because of the race for space of 40 years ago during the Cold War that all those things exist. The drive for miniaturization, the drive for lower power. I get a little passionate, I would say, is the politically correct way to put it, regarding those things, because I just don't even, it makes no sense to me. The reason we have hydroponics, the reason we have Tang, Tang was invented for astronauts. Give them some vitamin C so they didn't get scurvy. Right? What space exploration does is it forces us to optimize our technology at a bottom line level. I urge people who have those questions to Google NASA spin-off and look at how much technology every year goes into the world for the benefit of humanity, thanks to money spent and research done by NASA. And that's just NASA. That doesn't include all the commercial space research. That doesn't include the defense. That doesn't include the modern space race. And I will defer at some level, to the words of JFK. He talked about in the famous speech, that launched, the lunar program, the Apollo program, right? He said, we go not because it's easy, but because it's hard. Because in doing so, it will serve to measure our capabilities, right? What type of civilization are we? If we can go out there, we can then also apply what we learned by going and doing there to Earth. If we find extremely efficient power generation capabilities, you have to believe that that's going to end up on Earth. If we figure out how to, pardon me.
It's okay.
If we figure out how to generate power very efficiently, if we figure out how to grow crops with almost no water, all those learnings are going to be delivered to people here on Earth. And also the autonomy, the medical benefits, the ability to manufacture things that you can't manufacture because gravity is problematic. There's all these applications that are going to be enabled by going to space and doing things in space. And it's going to be critical that we realize that only by doing those things are we going to be driven to that.
No, that's true. That's true. So then the flip side of that is, do you think enough is being done around the globe to further this cause? You talked about fusion, source of energy from fusion reaction, going to Mars, discovering water on Moon, and so on and so forth. Do you think enough is being done to push science to that level?
I would say that no, and I'll be pointed in my remark in that I believe that fundamental research is underfunded around the world. What has happened is that there has been a trend towards applied. Everything has to be applied. Everything has to be commercial. And I fundamentally understand that. We need return on investment on research that's done. It's money spent, particularly when it's coming out of government budgets, which fundamentally come from the pockets of their citizens. At the same time, I have to remind people that the greatest inventions came from science that was not done for an application, but was done for science's sake.
Yeah.
You don't know what the applications are going to be. You have to go find new physics. You have to go find new chemistry. You have to go find new biology. And you may not know how it's going to be applied, but you've got to chase the discovery, because nobody had any applications for quantum mechanics when it was posited by Einstein, to the point where Einstein himself threw it out. And then other people said, actually, no, that's a good idea. And then got into an argument with Einstein, very famously. You know, Einstein saying God doesn't play dice with the universe. Well, it turns out he does at some level.
Yeah.
And none of that, all of that was purely academic until it wasn't. Until the transistor, until the photodiode, until the nuclear reactor and the nuclear bomb. None of it was applied until it was.
Yeah.
And that type of research is underfunded around the world, and particularly in the US. We have focused on industry and the startups, and they do great things, but we need the national labs. We need NASA. We need what are called the federally funded research and development centers, FFRDCs. We need the universities. We need to maintain that this university system in America is the best funded and creates the greatest creative output of any system the world has ever seen. And I'll be honest, Manoj, I am unapologetically an American capitalist. So, you know, I do think that we need to also apply it, and we need to get an ROI off of it, but we need to invest, and we need to enable researchers to chase the science rather than chase the application.
That's well said. Well said. No, I agree. I mean, science is what sort of makes our life better and pushes us forward as a species. Now, the other aspect, again, you know, bringing it a little bit back to the human level here, what I have found is that there are a lot of great researchers, scientists, engineers around the globe, and typically what I found is they are, you know, since engineers like myself, we are generally introverted. We don't like have the ability to express ideas and share ideas, get buy-in. I mean, you are very eloquent in how you present, but not everybody is capable of doing that. And because of the lack of their skill to connect emotionally, or you know, spread their ideas, their papers may not even get published, or they may not even get any attention. Do you see something like that happening as well?
I do think that there is space for better science journalism. For example, you know, what you do, Manoj, I think is great, because you bring people forward and ask them good questions to draw them out. You know, so if I'm eloquent, it's because you're enabling me to be. So thank you. You know, another somebody who's a colleague and becoming a friend, Michael Sheets of CNBC. He's a space reporter. You know, I think he's one of the better people to follow, because he's not sensationalizing, but what he's doing is he's talking about, hey, this is why these things are important. And I think there is space for science journalism to be better, to move it out of the realm of journalism for other scientists and move it into journalism for the general public. And what I think is so huge an opportunity is to bring the public closer to science rather than bring science closer to the public. To draw in the accountant, the marketer, the person working, you know, as a checker at a grocery store, to bring in the construction worker and bring some fascination to their lives. That is not a TV sitcom or some rubbish, you know, science fiction or fantasy series, but that is fascination with the world around them, that they can touch, they can feel. Right? People need to be encouraged to go out at night and look at the stars and realize that that's not just some random thing. That's not just art up there. That is real. That exists. You are part of that. You are whizzing around at so many 1,000 miles per hour on, you know, in the spiral arm of that galaxy that you're looking at. Right? We are on a spaceship, for God's sake.
Exactly.
So, you know, I think there's an opportunity to help people connect to science and to the natural world around them.
Yeah. Absolutely. Yeah. I mean, you brought up a very good point here that, when people from different walks of life, like accountants and store owners and all that, they understand these different realms. Like, for example, in my own life, just like you, I dabbled in so many different things, and
Right.
now I can put them together, even though, I have knowledge of science, which I can put in marketing, and, I have a knowledge of AI, which I can put it in different systems. So it's a fascinating way of looking at a world from different angles, and it starts to make a little bit more sense in a way.
I think so. And, it goes back to what we were talking about in terms of interdisciplinarianism. There's a really great book that I urge anybody really anybody to read, called The Medici Effect.
Hmm.
And it's written by a guy who dropped out of Harvard Business School to write it,
I see.
because he's so passionate about it. And he said, I'm onto something.
Mm.
And it's based on the concept of the Medicis of
Mm.
Florence, Italy, and the fact that they brought all these people together who were of completely different disciplines. And the basic concept in a nutshell is that the greatest, most interesting things happen at the intersection of
Yeah, yeah,
fields, right?
yeah,
And a lot of us, I know you we have this innate sense that that's true. But what's
mm,
nice about this book is it goes through, it develops it as a theory, and it helps give you ideas about how you can bring that into your own life and into your
awesome.
own and into your own business, what have
Yeah,
you.
yeah,
I mean, it can be relevant to anybody. It turns out um, that the drive-through for McDonald's, the drive-through concept was invented because one of the founders went through a drive-through bank window.
yeah, yeah.
He said,
I read that.
why can't I apply this to
Yeah,
my burger?
exactly. Yeah, yeah, yeah,
Right? Completely different industries,
yeah,
completely orthogonal, right? The one is food, the other is banking.
yeah.
But there was also an intersection point, which was customer service.
Mhm, mhm.
And that's an analogy that has no science in it whatsoever.
It's
What's
a
beautiful,
observation, just
yeah.
observation.
What's beautiful is when you do this in science. For example, years ago, Japan was developing some of its bullet trains, and they had to stop some lines or reduce the speed in the cities because of the wind hammer. So this is a big object moving at speed, that bop, 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 that you get when a train comes, right? And that was causing problems. It was breaking windows because of their elevated train lines weaving in and out of buildings, very dense cities, right? Tokyo, etc. What do you do? So it turns out they invited a biologist into their design meeting. And she said, well, nature has solved this problem. They're like, what are
Mm,
you talking about? They said, have you ever heard an owl?
mhm.
Well, yeah, who? No. Have you ever heard an owl fly? No. Well, there's a reason for that. And so what they did is they adopted the shape of the front profile of the owl in flight to the
Ah,
design of their lead car in the train,
nice, nice, nice.
and thereby reduced almost to nothing
Yeah,
that acoustic issue.
yeah,
And so there's a concept in engineering that is have an artist at the table
yeah, yeah.
in the design meetings. And so, these things are starting to happen, but I think, anything that we can do, you and I and others can do to accelerate the integration of this type of transdisciplinary, interdisciplinary thinking would be great.
Absolutely, absolutely. That's great. Now, one of the final questions. I know we are way over time. What do you make of the current situation? I mean, I think we went through a huge shock to a system last year, but I feel like there will be long term implications even after the vaccines and everything are sort of, we are out of this crisis, because of technology, because of what we think now, we are capable of doing without being always face to face and whatnot. What are your views? Do you think there's going to be some long term effects in how we live, work, play?
Oh, I'm certain. I think it's good in a lot of ways. And like anything in the free market, it's going to be messy. There's going to be some people that it affects in an unfortunate way, but in overall, I think it's going to lead to a greater quality of life
Mhm,
for a lot of people. It's going to enable a lot of people to, just purely economically move into areas where they can continue to deliver the value they need to deliver for their jobs, but take advantage uh, of different costs of living, etc. I also think it's going to be very interesting to see what happens to the cost of lab space. Because office space is not going to be needed as much, so all that's built up, and they're going to want to rent it out to somebody. So I actually think that there's going to be an opportunity to bring a lot of things back, and do certain things physically that had started to become cost prohibitive in population centers. But overall, I think it's going to be interesting. But I also think it's an acceleration of what was going to naturally happen over a decade, basically because of the shock. Has for once, something moved to the right in the calendar, right? You know what I'm saying, right?
Exactly.
Usually they move to the left, but for once it moved up, and it's going to be remarkable to see what comes of this. But I view it as tremendous opportunity, because it's exposed tremendous inequity, right? The difference in how people were able to move forward during the pandemic between those who could afford internet and who couldn't, or who had high speed versus who didn't, and those types of things is being understood. It's not fully understood, but we know that it is a major dividing line between how people fared. And so the concept of internet access as a utility, basically, is one that's growing. The concept that, hey, we need to rethink how we deliver education, is one that I think is tremendously powerful. Because I've always wondered how many Ramanujans have there been throughout history that never wrote a letter,
Absolutely.
right, and have been lost to history.
That's exactly what I was saying earlier with the introverted thing, because I find that everywhere.
Right, and so the internet is going to enable us to find all these gems around the world and put them in a place of apprenticeship with the best minds that we can, and that's just good for the human race.
Yeah, that's amazing. Thank you so much. Well, this has been a fascinating conversation. Thank you so much for spending this much time and sharing all the insights behind the scenes and the exciting stuff. I mean, I get excited. A lot of people may not find it exciting, but I get excited about this. So thank you so much for sharing all this. Now, before I let you go, can you tell us how people can reach out to you, how they can connect with you?
Definitely. Please find me on LinkedIn. It's /ZAALI. Maybe you can put that in the notes. You can also find me on the America's Future series YouTube channel. I host Space Talks with Z, where we've also hosted Manoj. So
that was an amazing conversation.
I'm sure you haven't had enough of him, so go there and get another dose. He had some very fascinating comments about how we can move forward together and work better. And also, please don't hesitate to find me via NASA as well, through their website. So you can just Google me.
Great.
So it's my pleasure to be in touch.
Thank you so much, Zaheer. Thank you so much.
Thank you, Manoj. Take care.
All right. Thanks. Bye.